Nice to meet you all. So for who haven't known me, I'm Queen, host of Eat Vietnam. And then first of all, we would like to thank you, Khyber, to co-host this workshop with Eat Vietnam. And also thank you for all of you guys come here and enjoy the workshop, the first workshop in Hanoi. And we also would love to have a chat and meet up with you guys later after this workshop to understand more about what you're doing and about the project that you're building. And we would like to also introduce the Ethereum Foundation mentor, speaker, and also from the Ethereum Foundation team to join this meetup today. Firstly, Barry Whitehat. Please give a big applause for Barry. And Dustin over there, yes, also from Ethereum Foundation. And we also have Karen from Singapore, Women Blockchain, and Wu also come here to support for this workshop. And thank you very much for your presence today. Thank you, Khyber team. Khyber team super support us, because we do it super last minute, to be honest. But thanks for their support, we make it happen very quickly. So, Eat Vietnam is a series of the workshop and event from August until the main event in November 25th to 27th. And the purpose of all of this kind of workshop, we want to connect the local dev team and also the global dev teams and other, projects, especially on Ethereum Foundation and Ethereum ecosystem. And the content we focus on layer 2 also. So that's why, also we have the first workshop with Barry Whitehat. He support and also focus on ZKP. And if you want to looking for more information about the workshop, we have the website Eat Vietnam, and also Discord, Telegram community will send you after this workshop with all the recap video, so you can check it out later. And now I give back to Barry Whitehat for the workshop. Thank you so much.
Thank you, Quinn. Is there a thing for the slides? Okay.
For the slide, whenever you need to next,
I'll tell you.
Yeah, he will do.
Okay.
And also the laptop.
Oh, it's here.
Just in case you need something.
Okay. Oh. Okay. All right, thanks everybody for coming. While we're getting the slide set up, I wanted to kind of try and get a idea of people's backgrounds. Who is here today to learn about, or who is primarily interested in scaling? Could you raise your hands? Okay. Okay. And who is primarily interested in privacy? Okay. Okay. Okay, cool. And who is interested in making applications as opposed to doing okay. Okay. Cool. Okay. Okay, let me get started. Yeah, so I wanted to talk today about quadratic funding and how it's an important tool for us to not only kind of show, not only to better support the ecosystem in a neutral way, but it's also really useful because it kind of helps us to deal with it kind of helps us to show our values to the rest of the world. That at the moment there's a lot of talk about cryptocurrency and scams and speculation and NFTs, and this is quite frustrating because it feels like we're sort of missing some of the point of why we're all interested in this space. That it's hard when the community is sort of growing, that when more people are joining, we want to sort of share with them our values and what we think is important. One thing that I think we all think is very important is for us to be able to support public goods, or to have some neutral mechanism to support public goods. And this is a use case that's a lot less controversial than the ones that we're more used to, than NFTs and DeFi. It's just basically people just getting together to fund and support projects that they're interested in. Who here has used quadratic funding before? maybe via Gitcoin grants or something, some other. Sure. Yeah. Should I start again? Should I go back to the start? No need? Okay. Okay, cool. So, yeah, so one of our priorities is to try and make these other types of use cases happen. So, like, one thing I wanted to see is, like, have some people here, like, are familiar with quadratic funding or quadratic voting? Like, maybe you use that with Gitcoin, or maybe you use that for the recent, like, ETH staker quadratic funding round. Has anyone used that before? Okay.
I used coins only once, but I didn't understand the quadratic.
Okay. Okay. I'll introduce that in a minute. Yeah. So, like, so there's a whole bunch of different tools that we use to do quadratic funding, and like one of them is called Maci. And Maci stands for minimal anti-collusion infrastructure. And basically, like, a big problem with quadratic voting and quadratic funding is that there's this issue of bribery. That, like, you're able to, like, trustlessly bribe other people to vote in a way that you want them to vote. And this turns out to be, like, very, like, it makes a lot of, like, economic sense to do this, which we'll get into in a minute. Okay. Okay, so before I talk about Maci a little bit, let me talk about quadratic funding. So, like, quadratic funding is kind of like a mixture of voting, and it's kind of a mixture of voting and donating. So basically the idea is that, like, we all get together and we want to fund a bunch of, like, public goods. And, like, public goods can be, so the definition of a public good is basically something that, like, that is, like, beneficial to everybody. For example, software is an example of a public good, or open source software is. And, like, I think that a public good is something where you are not able to say who benefits from it. For example, like, if I can say that, like, you get it, you get it, you get it, you don't get it, then it's not a public good because I have control over it. But, like, something like the Linux kernel is an example of an out and out public good, because you just publish it and then everyone is able to get the benefit of that. So, like, open source software is an example of a public good. And, like, we've been spending a lot of time trying to figure out how we're better able to fund and support public goods. Because, like, that's one thing that the Ethereum Foundation spends a lot of time doing, is to, like, give grants to the ecosystem and try to support these different kind of public goods infrastructure and initiatives. So, well, let's think about a little bit about the sort of tragedy of the commons and why these public goods don't get funded in the first place. So, like, basically the tragedy of the commons is basically that, like, if something is going to be beneficial to everybody, why do I need to be the one to fund it, right? Because everybody sort of says this to themselves and they say, oh, well, everyone's going to benefit from it, I'm not going to support it, right? And this is a tragedy, right? Because it really benefits everybody, but, like, nobody wants to be the one to support it. So, like, quadratic funding is a way to sort of bypass this mechanism. And what we do is we say that, like, we'll make it worth your while to donate the things that's valuable to you, because not only will your donation count, but we'll give you, like, an extra matching amount. Every time you donate, we'll give more. So that, like, that kind of breaks this sort of tragedy of the commons problem, because, like, when you want to support some public good, you feel a bit better about doing it, because it's not just you who's donating, you're getting the matching funds from someone else. So this is basically what quadratic funding is. It's like this idea of matching. And, like, the reason we call it quadratic is that, like, we match quadratically. So if you give a little bit, we give a little bit. No, if you give a lot, we give a little bit. If you give a little bit, we give a lot. And, like, the idea here is that we want to give more to things that, like, many people want, as opposed to we want to give, yeah, so we give more to things a lot of people want, and we give less to things that, like, only a few people want. And that's how it's kind of, like, that's the piece that's sort of like voting. Things that are very popular tend to get a lot of money, and things that are not very popular tend to get not a lot of money. And this is
a system for allocate the resource more efficiently.
Yeah, exactly. So it's a system to allocate resources more efficiently. Yeah, that's 100% what quadratic modeling is. Yeah. So like that's actually a great summary. Thank you for that. Right, so that's what we want to do. We want to make a system to allocate resources more efficiently. But the problem is that when we try to make a system to allocate resources very efficient or more efficiently, there's always this issue of bribery. Because if we're able to allocate resources efficiently, people are always able to kind of mess with that system and break that system. And basically what they can do is they can say, oh, I will bribe you in order to donate to this cause instead of this other cause. I'll give you all the money that you need to donate, and you just need to donate for me. And like in that case, that kind of corruption really breaks the system, because we've designed this thing that like lets us efficiently support public goods, but like bribery from outside the system is able to break it. So
Corruption is kind corruption.
corruption, exactly. Yeah. Corruption is a big problem. Yeah. So like this system kind of makes it impossible for corruption to affect the result of this kind of like system. Right. Yeah. So how do we do that? How can we prevent corruption? So the first thing that we basically, okay, so let's think about how corruption works. So if I want to corrupt somebody, I basically need to tell them, oh, if you do this, I'll give you this in return. I'll give you this much money. And like this arrangement is based upon the like, if you do this, then I'll do this. And like what the way that Maci works, the way that we make it impossible to corrupt people or to bribe people is we make it impossible to prove if you actually did what you claimed you would do. That's like the key of like how this all works, and we're going to get into that in a minute. We're probably going to get into like how we achieve that later, but like on a high level, what we do is we use zero knowledge proofs, you know, and this kind of like encryption to make it impossible to see exactly what any one person did. But we'll get into that later in the second half on the whiteboard. We'll start to explore. Okay. Yeah. So like.
Can you make it closer? Because like on there it's small.
Yeah, but it's really okay. Is that good?
Yeah, better.
Okay, sorry. Yeah, so basically what we're saying here is that we make it impossible to prove how you voted, and then, or we make it possible to prove that you did what you were bribed to do, and therefore a briber can never trust you because you can't prove it to them. You don't have some sort of evidence to show them that I did what we asked. Okay. Okay, so like when I first started working on this, I was unsure whether like bribery was really that big of a problem for like these on-chain voting systems, because like my intuition was that like, well, I've seen voting systems a lot, and it's very rare for bribery to really be an issue there. And I think that was because the systems that I saw were all off-chain. All of the, the systems that I saw were all off-chain. There was all, sorry, one second. So the systems that I saw were all off-chain. It was basically like paper and pen ballots. You would go and you would vote and you would put it in the box. And like those kind of systems, it's really hard to bribe people because it involves a lot of work, right? You have to go and find the person you're going to bribe, and you have to ask them, and you have to find a way to trust each other that like I am actually going to bribe you, and you're going to do what you're going to do what you say you're going to do, and then I just have to repeat that for many other people. Like this seems like in the off-chain world, bribery is just like prohibitively expensive because it's just like so much work to go and find people and then to actually execute the bribe. And the other thing is that like if people find out that I'm trying to run this like massive bribery campaign in the middle of like some kind of voting that could affect the result of the vote, I could get in trouble. It seems like that's just going to be really difficult to set up and to pull off.
Actually, people can on-chain approach, like somebody going to try to build the app and also allow people to use that app to vote. So the two problem is, I think it's the same. If you're using the approach of on-chain voting.
Sure, so let me just repeat what you said, just for the live stream.
Like,
Or-
That's one of those really your question.
okay.
But can you speak louder?
So I mean that adversary is going to use the same mechanism. They build an app and allow people to use that app to voting option. So the problem is will be the same for two cases.
You think so? Like
Yeah.
the problem with the, so let me repeat just to make sure I understand
Yeah.
what you're saying. So basically you're saying that like, yeah, but like in the off-chain voting context, an attacker could just make an app and like incentivize people to bribe. So they would go and they would vote and they would take a picture of their vote and they would submit that in the app and then they would be able to get bribed. Is that what you're saying?
Yeah,
Yeah.
they're going to building up an app to buy the votes from people.
Right. Yeah. That's. Yeah, I see what you're saying. I think that like, if I built that app, I would be really worried that people would be kind of like pretending to get bribed, right? Because I don't really have a way for them to prove to me that they got bribed or not. Like, all they could do is like I'm worried that people with like some kind of film background or something would kind of forge the ballot and the scenario, and they would kind of take a picture and they would submit that to the app. That like in the off-chain voting context, there's no way for someone to like prove that they did or didn't get bribed, or they did or they didn't do what you want them to do.
So what is the meaning of the blockchain? Blockchain is a sign paper and then send to the voting center.
So
What is the meaning of chain?
off-chain, yeah. Sorry. So the question is, what is the meaning of off-chain? Yeah. So off-chain isn't a cryptographic signature. Off-chain is like just like paper and pen ballots. That was the example that I was using. I think that like maybe you understood that off-chain was like just signatures that weren't verified on chain. Okay.
Okay, I get it.
Okay. My apologies. Yeah. So yeah, you can just keep that and give it to someone else if they have a question. Yeah. Okay. Cool. Right. So that's for the off-chain voting context. But like when we start to move things on-chain, or when we start to have cryptographic signatures associated with our votes, what you're saying becomes a lot more easy to do, right? Because you just, like in that case, all you need to do to bribe someone is to you can make a smart contract that does that, right? A smart contract that basically just pays if you send a signature that's voting in a certain way. So like that's my kind of bigger concern here, that like if we start to move voting on chain, that it can become really easily corrupted. That was one thing that was sort of difficult for me to grasp when I first started working on this project, because when I first started working on this project, I didn't really see that like off-chain voting is like considerably easier or safer than on-chain voting, especially because you have this concept of receipt freeness, that you're not able to prove to anyone how you voted, because all you can do is take a picture of your paper ballot and send that. But you can always like Photoshop or whatever, make a deep fake of the photo. Seems like there's a bunch of different ways that we could like attack or trick a briber who's trying to bribe us. So my larger point here on this slide is to say that like we have to be careful when we build these on-chain systems, because bribery will become a serious problem. I think that it's just a matter, like we've already seen some like governance attacks against DAOs where people were like bribed to vote in a certain way, and like corruption and things like that seem to be becoming like more and more pressing issues when we're thinking about DAOs. Yeah, so in order to be able to scale our on-chain voting, we need to be careful to account for these problems. Thank you. Yeah, so I already talked about this a little bit when I was talking about quadratic voting, but let me, or quadratic funding, but let me go through this again. So like the question here is like, why quadratic funding? Like, why is that important? Or why is that better than just regular voting? And like one argument is that like when you're doing like a regular vote, there's no, so there's all these arguments why it doesn't make sense for people to participate. One of the arguments is basically like, I am one of a person who lives in a country with 19 million people. My vote is basically meaningless. There's no way for me to affect the outcome of the vote. That's one thing where it's like, it doesn't really make a lot of sense for people to participate. And yeah, so like with quadratic funding, it's slightly different. With quadratic funding, we're able to give people like who really care about issues the chance to express themselves, and or people who really care about funding public goods a chance to express the public goods that they really care about. And basically the way that this works is that like we force people to donate in order to be able to signal how much something is worth to them. And that's kind of like put your money where your mouth is kind of thinking, where like if I'm gonna donate like $2 to something, that's a lot of signal of how valuable that is to me. And like we can make all these arguments about how like getting people to contribute money to things is a good way of seeing how much they value that thing, because money is like scarce and people are reluctant to spend money on things that are not valuable to them. The final thing is that like when we think about quadratic funding and talk about donating, there's always this thinking that like, well, but will rich people have like a lot more impact on the actual result? But the answer is that won't happen, because the matching funds are weighted quadratically. If a rich person donates $100, they get like a very small matching amount compared to someone who donates $1. For example, someone who donates $1 will get $1 matching amount. Someone who donates $100 will get $10 matching amount. And like it just scales like that. The more you give, the less that's actually going to be matched. Right, okay, so that's quadratic funding. And yeah, so like the way that I sort of think about quadratic funding and how it can help our world is that I think about like having this like neutral and censorship resistant sort of hierarchy of different quadratic funding rounds that are like happening all over the world on the same kind of cadence, that like 4 times every year we have like a whole bunch of quadratic funding rounds. One thing that like we didn't talk about yet is that like when we're doing a quadratic funding round, we need to have like a proof of individuality. And the reason that we need a proof of individuality is that people need to, because we have like one person, every person is able to contribute just from one account. We need to be able to limit the set of accounts that people have created. And to do this, we use like a proof of individuality. Yeah.
Proof of who? Proof of human.
Proof of humanity, yes. Yeah.
So basically KYC?
So not necessarily. So we can have like different kinds of proof of individuality. Like, oh, sorry. Let me just repeat the question for the live stream. So someone said, so basically KYC? And I said, oh, not exactly, because we can have different kinds of proof of individuality. We can do KYC, but we can also do like Bright ID, where your social graph is indicating whether you're a Sybil or not. Or else we can do some more advanced things with kind of ZKPs, like there's this really cool algorithm called Eigentrust that allows you to calculate scores in like social networks, similar to the way Bright ID does it, but in a private way. So like there's a bunch of different proof of humanity, proof of individuality algorithms that we can explore. So it doesn't have to be like off-chain KYC, we can have like other examples. For example, like one thing that we could do is we could have like a quadratic funding round for ETH Vietnam. And we could say anyone who attends ETH Vietnam is an individual person, and they're able to contribute to the round. So like we can do things where like the proof of individuality is not really strong, but we can still have some like benefits. We can still have some like pretty good results with those systems too. Like we don't have to be like 100% KYC in order to be absolutely certain that everyone is an individual human. Cool. Any other questions?
Actually, there.
I think that there may be some problem with it because
so I remember that's
long
time before.
a long time before is the last
People do
with the that wrong
with the T-Base.
tibay.io, and then the hacker going to get a GitHub account to get the address. So what do you think about it?
Yeah, so I think that that's a problem with like proof of individuality rather than with quadratic funding. But like what you're getting at, I totally agree with. Proof of individuality is really hard. It's really hard to have a way to be sure that like a different person is actually an individual human being. That like there has been attacks like that before, and there will be in the future. And I think that like we need to build better proof of individuality systems, and in the short term we should just be like adaptive when we're running these quadratic funding rounds. If it's clear that someone signed up with like 1 million accounts, we can adjust and change what we're doing. I think that like probably what we should start doing is to start and build a system where it's impossible for an attacker to make more than 10 accounts, and then start to go down and down until we get to the point where like it's also really hard because it's this trade-off of like how difficult it is for legitimate users to sign up, and how difficult is it for an attacker to fill up the whole state. But like I totally agree with what you're saying. Like proof of individuality right now is not very advanced, and that's something that we really need to spend more time trying to improve. Yeah. Cool. Yeah. So, any other questions? Okay, cool. So one of the key things we're trying to do with Maci and QFI is to try and make it as easy as possible to run these rounds. And like what you're saying is like one part of that. Having like this easy KYC protocol or process in place is very important. Yeah, so like we're trying to start doing more of these rounds by doing like just many local rounds around the world. We did one in Barcelona, we did one at East Prague, we did one in Honduras, and like we're hoping to do more and more rounds in different places. Another thing that we need to do is improve the security of Maci, the quadratic folding system that I'm going to talk about later, because security is such an important requirement here. We want to be in a position where we're able to run these rounds in like all kinds of different places around the world, and in order to do that we need to be able to have like more security and more confidence in the system that we're building. Yeah, another thing that we need to do is like share and spread the idea of like quadratic funding and why it's important for why it's an important tool for communities to kind of fund public goods. Cool. Yeah, so that's our plan with this quadratic funding round incubator that we're running. We've already run one round in Honduras, and we've done a couple of others. Maybe you all heard about the ETH Staker quadratic funding round. This was a funding round for the ETH Staker community. They're like people who run staking infrastructure on Ethereum, and we did a quadratic funding round in partnership with them in order to like support the local quadratic funding public goods. We're trying to do like some non-crypto focused rounds. So far we've been exploring like different places that we could do those that are not just about like the crypto stuff, but also about like different kinds of things. Yeah, so this is our plan for the rest of the year to sort of scale up the number of rounds that we're doing. Cool. Yeah, next slide. Okay. Yeah, so okay, let's start to think about like the Maci stuff that we want to do. So let me briefly describe how Maci works, and then we can talk about some of the improvements that we can make. Right. Okay. So okay. Right. Okay. So now is the ZKP stuff. So we finished all of the preparation. Right. So okay, it seems like it's a hard problem. We have this system where we want people to be able to vote, but we also want it to be impossible for them to show other people how they voted. So how can we do this? It seems like, okay, so these are the people who want to vote, and I suppose that this is their votes. And then we have this role of like a coordinator. And the coordinator kind of takes the votes and decrypts them. Yeah. So the coordinator takes the votes and decrypts them. And from there, we kind of like process the votes into a Merkle tree. Okay. So after the coordinator processes all the votes, they do the like tally step where they calculate the result and share it. Okay, cool. So like when someone is voting, what are they able to do? So there's two actions that a user is able to take. The first action is they're able to vote, and the second action is they're able to like update their public key. They're able to update their public key. Okay, so like basically we maintain this Merkle tree of all of the different public keys. The user is able to all of the different public keys of each user. So each user has a leaf inside this tree, and when they update any given leaf, we give them, yeah. So. Right. Okay, so we have Merkle root here. So this is the state of the system at the start. So each user has like a single leaf inside this tree, which is like their public key. I'm gonna hold on. Let me just draw this a little bit bigger.
Larry, sorry, can you make bigger, please?
Yeah. Okay, so okay, so in this system, everyone has a public key that's associated with their leaf. So each user in the system has a different leaf in this tree. And when the user wants to make a vote or command, they sign their vote and then they encrypt the signature of their vote. So we have this encrypted vote. We have an encrypted vote that gets passed to the coordinator. So the coordinator then creates a ZKP that they've done a whole bunch of different things. The first thing they do in the ZKP is they decrypt it. They decrypt the encrypted vote or command. When they decrypt it inside the ZKP, and then they update the leaf according to the rules, according to what that command says. So, and we prove all of this inside a ZKP. So, yeah, we prove all of this inside a ZKP. So, what do we prove? So we improve the decryption, and we prove the tree update. and that's it. Okay, so this is what's happening inside our ZKP, and like let's think about the situation where there's a briber who wants to bribe a user. So we have our user here. This is our user. Okay, this is our user. They created a vote, and there's a briber who's kind of like observing. There's a briber here who's observing the vote that went on chain. So in this situation, is there any way for the briber, or is there any way for the user to convince the briber that they bribed in a certain way, or that they voted in a certain way?
They can show something, like if they know the leaf, they can try to open it.
So they don't know the leaf. So like, sorry, let me repeat for the live stream. So like Nam said that, oh, if they know the tree, they can open the tree. They can just show them that like, this is my vote. Can I have my bribe, please? And like, that's true, but they don't know the tree. That's the only person who knows the tree is the coordinator. Only the coordinator knows all of the leaves inside the tree, and so it's hidden from the users. The users aren't able to show what's inside. Is there?
So why does the user need to update the public key?
So the user the user has two options. Oh, sorry. The question is, why does the user need to update the public key? The user has two options. They can vote or they can update the public key. We give the option to update the public key in order to prevent bribery, which we'll get into that in a little while. There's still a couple of steps first before we get there. There's like a couple of other attacks first that we have to kind of solve, and then we can solve that one. Any other ideas about like how the briber can successfully bribe the user here?
You can prepare the key for the users and let the user vote.
Oh, sorry. Whoa, sorry. That's too loud. Yeah, that's a very good point, and that's a very important attack. That like one way that the bribe could succeed is that instead of voting here, they could do the update public key. They could do the update public key for the user, and when they update the public key, they just set the public key to the public key of the briber. But like my question to you is that how does the briber know that the public key has been updated correctly? Right? Because remember, the user and the briber, they don't know the state of this tree. They don't know all the details inside the tree, but there is a way for them to know.
So what does a briber can access here? Like,
So, right.
Which one he can, like,
So, okay.
all these things, which one he can access?
Right. So the briber can see all the encrypted messages that get put on chain, and they can't see this tree. They can't see like inside the ZKP, and they can't see the tree. All that they can see is the list of encrypted messages.
So I assume that the user use the coordinator's key pair to encrypt.
Yes.
So he can just show all the randomness he have with the encryption.
Yeah.
To the briber, and the briber can do the encryption himself and check that it's correct.
Exactly. So the first thing that we can do is that the user who wants to be bribed can show the plain text to the briber, and then the briber will be able to encrypt the plain text for the coordinator's public key and see that that's actually the text that was included. So does that make sense? So like, let me just repeat just once more. So the idea here, let me draw it because it'll be nice. There. Okay. Right. So we have two people here. We have the user, and we have the briber. The user has this command. right? And the user wants to, and the user just encrypts this command for the coordinator's public key. They encrypt the command for the coordinator, and they get out this like, kind of like encrypted ciphertext that's really difficult to read for anybody else. So the user who wants to be bribed, what they do is they share this with the briber. They share this plain text. And they tell the briber, I encrypted this for the coordinator. If you do the same thing, the result will be the same, and you can believe me. So they do. The coordinator the briber takes the coordinator's public key. They do the encryption, and they find out, oh yeah, it's exactly the same. I know the text that they have encrypted for the coordinator. Any questions so far? Yeah?
Do the encryption actually necessary? Like what people try to replace the encryption step with the blind signature?
Sorry, could you say that again?
That is using the blind signature.
The blind.
Vote,
Mm.
and then the community don't need to decrypt the message.
So let me repeat just to make sure I understand what you're saying. So
User going to using the blind signature to vote.
So the user is using the blind signature to vote. So like, what do you mean by blind signature? Is that like the text that gets encrypted?
It doesn't need to encryption.
It doesn't need to be encrypted. Oh, so basically you're saying, well, we don't need to encrypt the ciphertext because it's basically meaningless here, right? There's no point in encrypting the ciphertext because you can always give it to a briber and they can encrypt it as well. You can always show a briber that, look, this is my ciphertext. See, this is how I voted. And like, that's a very good point. And the reason why we need the encryption is for the next step. So far, we've been operating in a system where we had just a single voter. We just had a single encrypted message on chain. But in reality, we'll have many different encrypted messages on chain. Okay? So this is message 1. This is message 2, message 3, message 4. Okay. So let's take message 4. This is message 4. It came from this user here. Message 4 came from our user who wants to be bribed. And the user who sent message 4 basically says to the briber, he tries to repeat the argument we've made already, right? Sorry. He basically says to the coordinator, hey, look, here's my plain text. You can take this plain text and encrypt it exactly the same, and you'll see that my message in message 4 is valid. You can see exactly what I've done at message 4. And they'll give this to the coordinator, and the coordinator, they'll give this to the briber, and the briber will say, oh, but I don't believe you. And like, does anyone know why the coordinator, the briber wouldn't be able to believe them in this context?
Why do these messages appear?
Ah, exactly. This message comes first, this message comes second, this is third, this is fourth. When the coordinator is processing this message, these 3 messages have already been processed. So it goes like this. So this is the order in which they get processed. So I see what you're getting at here. The reason that the briber could never believe the user in this case is that the briber doesn't know what happened here. The user could have submitted a message here that made the final message invalid, right? Because we have this ability to update the public key. right? So any one of these messages could have been public key updates. Yeah. Okay, let me check the time. Okay. Okay, cool.
Yeah, but like can't the user open all his messages to the driver?
Yeah, he can, but he's not. He didn't make all these messages. Like, these messages are coming from other users.
Because from all different.
Yeah, because
Yeah.
basically the user cannot prove to the bride that these are all my messages, I have no other messages.
Yeah.
Okay.
Yeah. So like as soon as you have like a single message on chain that can't be decrypted, then the briber can't trust the user anymore. Like if all of these messages were from the user, then they could have a trustless bribe. But because they're not from the user, there's no way for the coordinator to know which ones are which.
So basically, that the user need to secure their public key also. Because if they leave the public key to other one, they also put that the same result.
Right. So basically, your question is that like basically the user needs to like okay. So like you're asking, what if the user gives their public key to the coordinator, or are you asking something else?
Maybe this guy, they know the public key from the primer give to me, and then he also proved that that vote is that from him, not from me.
Right. Okay. So like basically you're saying like what if a user gets another public key from a different user and basically pretends to be that user and say, hey, this is my vote, I did this, right? Yeah, I suppose that they could do that, but like, is that going to be a bribe, or is that just going to be like?
No, maybe they just want to prove to someone else, but maybe they do another vote, but they prove to someone else that I vote another one.
So that's an interesting. I see what you're getting at here, and it's an interesting attack. So basically, the attack that you're saying, let me just to make sure I understand correctly, that like, you said that like, okay, I believe you in this context. It's gonna be impossible for the user to convince the briber. But what if the user just sells their public key to the briber? What if they just say, here's the public key, here's my public key, you can have this public key? Like, could the briber trust that? Is that what you're saying?
I just assume that someone else got the primer, and they also do the same the encryption, and then they just prove someone else that I took that one, but he didn't.
Right. So like a user is trying to so like in this context, a user gets someone else's public key, and they basically take that public key, and they use that to show the briber that like, hey, I'm user number 1. This is my vote. But like, right, they could do that, but like, why would the users share their public key with that?
No, I mean that they also need to secure that public key. Instead that they also need to secure the private key from the beginning.
Right. Okay, yeah. I hear you. Like, so basically what you're saying is they need to secure the private key. Yeah, that's true. They need to secure their private key. If their private key gets leaked, a couple of different things can happen. You end up having this sort of race condition where, let me draw it a little bit. So like, we have to think about this in two contexts. Let's think about it in the context of like, first, a user just loses their private key. So a user loses their private key to themselves and to some attacker. This user gets hacked. So both of these people are able to interact with the system, and they're able to like change it in whatever way that they want. The first thing that they can, so you end up like, there's a couple of different layers here. The first thing to think about is like, well, who's going to be able to vote? It seems like both of them are able to create like valid encrypted messages, but it'll basically be a race. whoever's message gets processed first will update the leaf in the tree, and then that will be the final. Then the other user won't be able to. So like both users do an update public key. Both users try to update their public key. Both users try to update their public key. They get the encrypted message. They both go on chain. And basically, whichever one gets on chain first is gonna be the valid one, and the other one is gonna not work. But like one interesting thing to recognize here is that like in this case, this user might never know that that happened. They might never know they got hacked because they don't know the state of the tree. They don't know what kind of commands have been processed because they don't know what all the previous messages are. So like we end up with this system where like you never know if you got hacked or not, which is kind of scary, especially if you're voting on things or doing like big quadratic funding experiments. So like, and it seems like it would be nice to have a receipt, but like as soon as you have a receipt, then you're able to use that to get bribed. So that's, and like, okay, the other way that we need to look at this attack is what if a user shares their public key with another user, with a briber? In this case, it's just a user and a hacker. But like, what if the user like voluntarily gives their public key to a hacker or to a briber? So we thought about this before, and like basically we said that like if at any point here you give your public key, if at any point after the first message you give your public key to a briber, then the briber will never be able to believe you if it was actually a valid public key or not. But if they give it at the start, at the sign-up time, then it's possible for them to believe you, right? Because they know that like no messages have been processed. So this attack becomes quite serious, and it's at sign-up time. It's when I'm joining the group, I say, oh, I want to sell my account. Here's the credentials for my account. You can take this and use this for whatever you want. And these credentials are basically given to the briber, and the briber kind of takes those credentials. But they don't have certainty that they'll actually own the leaf because of this. The user and the coordinator both have the public key in this context, so they have this race condition. So the user and the briber both have the public key, so they have this like race condition where the user and the briber are trying to compete in order to get their commands on chain first. So, check the time.
Why don't bribers try to bribe the coordinator?
Yeah. Okay, they can do that. That's yeah. So there's two things to talk about there. So the ordering of transactions is not handled by the coordinator, it's handled on chain. So like they wouldn't be able to bribe the coordinator. They would have to bribe the like Ethereum miners or whatever, or sequencers or stakers, whoever is ordering the transactions. They would have to bribe them, but they could do that. The other issue that we need to think about is, right, so we talked about all of these different attacks where the user was trying to attract the briber, but what about if the where a briber is trying to bribe the user, but what about this coordinator person? Like, wouldn't they be able to bribe the user? Because like, basically they know the whole tree, they know the whole state of the system. And the answer is yes, like the coordinator is able to bribe users. And like basically what we do is that we've broken it down such that there's only like a single person who's able to do this bribing. Yeah. Yeah. So.
So 3 person can do the right.
Sorry.
You said like there are 3 people who can do the.
No, no, there's one person. There's the coordinator. Yeah. Well, I think the coordinator would have to work with the user, but yeah, 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 yeah. Cool.
Can I have a stupid question?
Of course.
So, I am a user. Voted. My vote is encrypted. So after that, can I see how I voted on chain?
Right. So you can see that message. So when you encrypt your vote, you can see this message, whichever message it is, but you can never be like 100% confident that, well, you can be 100%. So the answer is yes. You can see the question.
Snapshot? There is a snapshot?
Snapshot.
Snapshot, yeah.
Ah.
So after I voted, I can see my vote.
Right.
Yeah. In this system, can I see the same thing?
So the question is like when you're using snapshot after you voted, you can see your vote.
Yes.
In this system, can you do the same? No.
Can I see the same?
No.
No?
You can. Okay. You can see. Okay. So I suppose that you can. You can see. You can see this. You can see what you've done, but you can't see what other people have done.
Okay, that's enough.
That's enough. Yeah. I think it's enough too. Yeah.
Okay.
Yeah. I'm sorry. It was a little bit complicated a minute ago. I was trying to get at the nuance of like the system as a whole. But like users can see their votes. They know what they've done and they know what they've done. Yeah.
Do the like the organizer and the coordinator can change or remove my votes?
Ah, that's another important question. So the question is, can the coordinator change or remove your votes? And the answer is no. And that's why we use the ZKP here. The ZKP here kind of prevents the coordinator from like ignoring any votes or not processing votes in the correct order. So the ZKP is basically like limits the coordinator and what they can do. The only thing the coordinator can do is to refuse to reveal the final result. Yeah, they can, if like, so there is some like annoying situations where like after the round is done, the coordinator is just basically like, no, I'm not going to reveal, I'm not going to process all the votes, I'm not going to reveal the result. But that seems like it's okay, we could just do the round again. It's just slightly annoying.
So I have the follow-up question.
Sure.
Like the coordinator decrypt the votes,
Yeah.
and then they try to reset that vote and do not include in the reset.
No, so they're not able to do that. The votes are put on chain. So there's a smart contract on chain. If the coordinator wants to affect the number of votes or the order in which they're processed, they need to basically affect the ordering of transactions on Ethereum, which is hard to do. Like basically a censorship attack against this is a censorship attack against Ethereum, if you want to prevent users from participating.
So the ZKP is where is ultra plumb coming?
Yeah, so like that's some of our, yeah, maybe we'll talk about that after the break. Right, so like at the moment we don't have a ultra plonk ZKP, but like we're working on including it. So let me talk about that after the break. So we'll talk about some of the scaling challenges that we see when we're dealing with this, and we'll talk about like some of the things we can do to improve it. And like some of those things will be about ultra plonk, but it'll be very, very little, I'm afraid.
Sorry?
It'll be very little. We're not going to go so deep on ultra plonk stuff today.
Okay.
Yeah.
So, yeah, I have a question. So right now, what is this coordinator? Is it a machine?
So yeah, so like the question is like at the moment, what is this coordinator? Yeah, it's a machine. It's just a AWS, or it's just a pretty beefy server because it has to make a lot of ZKPs. But it's effectively like a person or a trusted entity Like someone has to run the server, so like that's kind of where the trust comes from. But yeah, it's just a computer.
So if this machine is compromised, there is no privacy.
If this machine is compromised, there's no privacy. Yes, but yeah, there's a couple of ways that we can add privacy inside our system. And like the other thing we can do is when we're doing the proof of individuality sign up, we can have a ZKP at the sign up time. So so you don't know like the connection between like a user and the actual votes. But yeah, privacy inside Maci is important.
What I mean is that, so like the encryption is done at this machine.
Yeah.
So if somebody cracks into the machine, they basically see the encrypted message.
Right. So if you get the coordinator's private key, you see all the messages. Yeah, you basically become the coordinator and you're able to bribe people. Like once you get the coordinator's private key, you also know the state of the whole system. Wait, let me think. You don't know the state of the whole system because like we have this thing where like we have a special leaf in the tree and we have a random number there. We write a random number there all the time. And like the reason, every time we update the state. And the reason that we do this is that like a lot of the time our commands fail. A lot of the time a command is processed and like one of the checks that we're trying to make fails, like a signature check. And when that fails, we don't update the Merkle root. The Merkle root stays the same. And if the Merkle root stays the same, then an observer can see that like, oh, that didn't work. That whatever happened here didn't work. And like that just reduces the like number of messages that could potentially be other users doing things. So in order to prevent that, we write a random number to the tree, to one leaf in the tree every single time. So you don't, like if you hack the coordinator, you get the private key. You get the private key, but you don't get the random number. You don't know what the random number is, so you don't know the rest of the state of the system. But like that doesn't really matter. You can still bribe people though, right? Because you know all of the valid messages and you know all the invalid ones. You just don't know the tree. But yeah, okay, that's a yeah.
I mean, basically, if you get the private key, right, you can just reprocess the whole history.
Yeah. If you get the private key, you can process the whole history. Yeah. So like basically, I see this as less a private application, and it's more of a way to have like bribery resistance. I think that the privacy guarantees here are like a lot weaker than what we're used to. Like with like ZKPs, we're used to having a privacy of like you have to mess up in order to use privacy. But in this case, like other people have to mess up, which is not as good.
I just think that privacy is important if you want to receive freebies, right?
If you, yeah, right. So privacy and receive freeness are inherently connected. Like this is kind of like a stronger case where you want to make it impossible to even show anyone. You want it to make it impossible to lose your privacy, even if you want to.
I'm just thinking that, for example, if you make this coordinator a trusted hardware, like if you are running the machine with Intel SGX.
Yeah. So the idea is to use SGX to run the coordinator, and yeah, that will definitely improve the security guarantees. But like, yeah, I just don't like to build things that are like, oh yeah, Intel's probably honest. But no, but it's definitely better than the status quo for sure. Yeah, the status quo right now is just a big server. But yeah, like the thing I would be concerned about is the making the proofs inside SGX might be very expensive.
I think the security of the coordinator depends on the user, who the user going to send the message, and how the user sends the message. Like if the user sending the message direct to the coordinator, it can be a problem because if they write the message on chain.
Yeah. So let me repeat. So like what you said was basically the security of the coordinator depends upon who is able to talk to the coordinator. If the user is talking to the coordinator, giving the messages, it's bad because they have like access to the coordinator, and like in an ideal world they shouldn't even know where the coordinator is. Yeah, I totally agree. So like in the status quo, the user doesn't talk to the coordinator, but we are working on an improved version to scale. And in that version, the user does talk to the coordinator. But yeah, it's definitely something to consider when we think about security guarantees. Yeah.
So how efficient and expensive is SGX nowadays?
I don't know. SGX is, I'm not sure. So like the latest thing I heard about people doing with SGX, sorry, the question was like how efficient is SGX nowadays? The most important, like the biggest thing I heard people doing with SGX was using SGX to do like a trusted setup for some of the bigger ZKP circuits. I think it was like Polygon Hermes did their trusted setup inside Intel SGX, but unfortunately, 0-day was found after they did the setup inside it. So like theoretically, they could have known about that exploit and executed it before it was published to get the you know, yeah.
They can just redo it again.
They can just redo it again. Yeah, but they have to redeploy the contracts. Yeah.
Oasis Network also use SGX for their private smart contract.
Oh, I think so the question is, did someone use SGX for their private smart contracts? Yeah, I think a secret network or something did. Oasis? Yeah. Okay. Yeah, it's possible. I don't pay a lot of attention to the trusted hardware stuff. But yeah. Okay, so let's have a break. There's some food and we can have some chats and then come back. We'll talk about scaling. Cool. Thanks, folks. I'm good. How are you doing?
I was advancing the slides for you.
Thank you.
I should like double skip a couple of ones. I skipped and then you skipped as well.
Yeah, no, there's some I wanted to skip. Those slides were not the best slides for this audience. Okay, let me go and chat a little bit. Let me go and chat a little bit.
Last minute today, is there any source that I can read more about this like quadratic funding and ZKP?
Oh, yeah, for sure. Are you interested in doing quadratic funding stuff?
Actually, it's very new to me.
Okay.
So I really want to read more into it.
Okay. How can I contact you?
I'm sure you have, what kind of messages you have?
Telegram?
Yeah, sure.
Oh, I don't have the QR code thing. Let me type my username in.